Now, so far, we talked about, this is the KPZ equation, right? And one should really differentiate the equation from the universality class. The equation is just another thing in the universality class, but it's a sort of continuum model, as opposed to the other ones, which are all discrete-like things. Now, the first problem, of course, is that the equation is not making any sense, right? Because the solutions we saw last time are supposed to locally look like Brownian motions in X. Okay? Actually, even immediately, no matter how smooth initial data you start with, for any positive time, it's going to look locally Brownian. Okay? Same Brownian motion, same local variance. So, so this thing can't possibly make any sense. So the question is how you're supposed to even make sense of this equation.
And what if you decide you wanted to regularize your noise?
Yeah, then it's fine. Then everything's fine. And in fact, it's not even, you don't even have, of course, if you regularize it in space and time, then you just have a function, and then you've just got a solution. There's nothing to do whatsoever. Everything's completely well defined. In fact, if you just regularize in space, it's already okay. Yeah. So this Ito calculus can handle that. Okay? So it's still white in time, but it could be regular in space.
You don't do that because?
Yeah, so that's a good point. So, so why not do that? Well, here's the thing. Because the equation's a magic equation when you don't have the epsilon. See, look, if I put in the epsilon, okay, so suppose I have this. Maybe I have the epsilon just in space because it's easier. And then you say, well, what's the invariant measure? Good luck. That kills it already. That's actually a question that physicists were asking.
I think that's an interesting question.
Yes.
But there are ways to discretize this so that to keep the Gaussian invariant.
You have to do it in a special way. Well, actually, if you,
I guess they're integrable and they're non-integrable type of regularizations, right?
exactly. If you want to do that, you know, it turns out there's something, you can do something special. You can do this. I'll write it as epsilon prime. If you do that, now epsilon prime, it turns out what you should do is you should use one smoothing kernel for this, and then take that smoothing kernel and convolve it with itself to be the smoothing kernel for this. And solve? No. I didn't say.
Okay.
But smoothed out Brownian motion is invariant.
Oh, so and then can you make statements about what happens from there?
Oh, I didn't get that far.
Well, that's already very interesting.
Yeah. So okay. So you know, you got to do special things, is what I'm saying. Okay. So okay, but you know, the reason you don't do it is because, you know, we've got some sort of perhaps integrable system, and you don't want to break that, right? So that's why we want to try to make sense of this thing.
The other system's even nicer than the one you just described.
Why is it nicer?
Because you've still got your invariant measure. What's wrong with it?
But I don't know if it's integrable.
How do you know that? How do you know
I can't compute anything about it. I can compute the invariant measure. That's it. Maybe it will turn out to be. I don't know. Okay. So how do you make sense of this? Well, actually, we sort of learned last time that there's two objects. There's the h and the z. So z is this e to the minus h. Now, okay, don't worry about the minus sign. The minus sign is easy because minus h and h is the same thing. But here I just want to write e to the minus h. So this is like the partition function, and this is like the free energy, right? It should really have been called f, but some h is for height. So so this z, you could try to write an equation for it. Now, you want to write an equation for z, then you better smooth out this guy. Let's take this, let's just pretend this is a smooth function of space and time, then it's easy. Then you just get dtz equals a half dx squared z minus xc times z. Okay? And xc here, of course, is xc of t. Xc is xc of t and x, and it's white, space-time white noise, right? But okay, but this transformation, this is the Hopf-Kohl transformation. Of course, that's illegal. That's completely illegal. So what's the truth? Okay, actually, we take this to be our fundamental equation. That's the stochastic heat equation. And for a reason I'll just describe in a moment, the stochastic heat equation turns out to be well posed. It's a nice guy. Okay? So this is very well posed. And then we can just define KPZ to be the log of the stochastic heat equation, or minus the log of the stochastic heat equation. And that's the definition. It's the definition. So usually that's called the Hopf-Kohl solution. The Hopf-Kohl solution. Solution of KPZ is H equals minus log Z, where Z solves the stochastic heat equation. Okay, so first I have to show you why that's even better, why this is better than this. But here's the key thing. If you solve this, okay, and take a log and apply Ito calculus, you don't get this. It's false. You get this thing minus infinity. The infinity is the Ito term. Now I'll be more precise. I'll make the statement a little bit more precise. So this is a stochastic PDE, and any stochastic PDE worth its salt means that you should regularize the noise and then remove the regularization. So we take this guy, we regularize the noise, then you get a Z epsilon. Okay? And regularize, just for convenience, will always mean regularize just in space, because it's better. Okay? Then this is not difficult to make sense of. Okay? That's just standard Ito calculus. And now you can take a log, and you differentiate it, and you're just using a standard Ito's formula. And you will, honest to goodness, so now there's a Z epsilon, and I define H epsilon like this, and then you'll, honest to goodness, get this. And you'll get C epsilon minus 1. And the C is just like the L2 norm of the convolution kernel. Okay. So that's what you mean that KPZ with the infinity there is what you get from this. Does that make sense? Okay. Yeah. So the honest way to write KPZ is minus infinity, and the point is that the infinity that you have to subtract from that thing is a sort of very well, it's like infinity you have your hands on in a very, very clear manner. Okay? So that's the definition of the solution. Now, of course, that just begs the question, why is this any better than that, right? Okay. Well, okay, so let's start with dtz equals dx. So just without the smoothing, xz. You say, well, why is it better? Somebody should say because it's linear, right? Yeah. Okay, so I actually want to make a point that has nothing to do with it. Sorry? Sort of. It's sort of linear, all right? Right. It's not really linear. It's linear in the initial data, but that's not your problem. Your problem wasn't that this thing was nonlinear in the initial data. Your problem is it's still nonlinear. What you're trying to do is you're trying to solve for Z in terms of the noise. So it's still nonlinear. So the fact that this one's solvable is more of a miracle than that. It's actually something, there's some special structure to it which makes it solvable. So how would you try to solve this thing? When you try to solve it, well, first of all, I'll just write the thing in the way you're supposed to write it. You're supposed to write it as an integral equation. Because, of course, this makes no sense as it is, right? You've got this distribution, you're trying to multiply it by something. Nothing's making any sense. But if you write it as an integral equation, well, then you have some hope that it's going to make sense. So P's, again, are just the heat kernels. So that's this fundamental solution. The heat equation, and there's okay, X, C, S, Y, Z, S, Y, Y, D, S. And you have some hope that you can make sense of that last thing as an Ito integral. Okay? So this thing's an Ito integral here. And so that's actually the definition. Now, suppose you actually wanted to solve it. So here's the thing. You can actually just solve the thing. Let's take, just to make things life easy, let's just take z0 to be a delta function and just try to solve it. Okay? So if we want to try to solve it, what would you do? Well, you just guess. Well, what's my first guess? My first guess at 0 level is ztx is just equal to pt x, right? That's a 0 level guess. And then the next guess would be that z1 tx is, well, I'll take this ptx. So here, if I make that a delta, let's just write it like. So I've made it a delta, so this is your equation. Okay? So the next guess is that, well, you would try to put in your first guess in here as the first guess, right? So your first guess is in terms of the guess before, right? The guess before is just psy. So you just get ptx plus 0 to t, pt minus s, x minus y, psy, csy, dy ds. Okay. And now you just keep going, and you'll get, what do you get? So you get the nth step. So each time you do it, you're going to get one more noise term multiplying the guy before. And you get something like this. So you get this summation, k equals 0 to n. You get an integral. Integral over r to the k. And then you just get, well, what are you going to get? You're going to get this probability sy, p, sy, and then another p, and then another p, and another p, and another p. I'll just call that p s1, x1, s2, x2, and then all the way up to t0, and then you get c s1, x1, to c s, just make sure I got this right, c sk, xk, yeah. X1, dxn, ds1, dsk, sorry. Okay. So you just get that. And these things, well, they're just these products of these p's. It's actually just the transition probabilities of a Brownian bridge. Transition probabilities. So it's just a very explicit thing. And of course, well, what happens is z, you want n to go to infinity. So when n goes to infinity, you just write this. And the only thing is you have to prove this series converges, right? But actually, the series converges very, very easy because this is just a Wiener chaos expansion. And so the L2 norm of z is just the sum of the L2 norms of these guys. And they're just computable things. It's very easy to check, and the whole thing converges, and everything's just fine. So you can just solve it. That's the amazing thing about that equation.
You do that in any dimension?
Yes. No.
Well,
No. No, it diverges. It's only in L2 in one dimension. It doesn't converge.
oh, because it's short range?
Yeah. Even in 2 dimension, you just get these log singularities. Everything goes wrong. Okay. So, of course, if you smooth out the noise, you can do it. Yeah, there's no problem. Yeah, sure. It's the structure's still there. Yeah. Okay. So, okay. So good. So that's why you can solve this guy, and now you have the existence uniqueness, and no problem. Anyway, so you just take log of that, and that's the h. Of course, this doesn't really help. It helps for some things, but okay. Now, one thing I just want to point out is you could try the same thing for the KPZ too. So how would you try it for KPZ? So if you try it for KPZ, you get your first guess. I mean, you have to be a little intelligent about what's going to be your first guess and what's going to be your next guess and stuff like that. But so your first guess for KPZ is you want to solve this guy. See, well, that's easy enough. You can solve that. That's just an OU process. So your next guess is dth1 is a half dx squared h1 minus a half dx h. So you should use the previous guess in the nonlinearity, right? Plus k. Now, you've solved this guy, so you can compute this guy, right? Now, if you compute that guy, you, of course, you just get infinity. And it's exactly the infinity up there. Exactly the infinity up there in the sense that if you do this with an epsilon and you compute this, and you get exactly the same c epsilon minus 1. Exactly that thing, so you have to subtract off infinity. That's okay. Now you keep going. The only problem with all this is that, unlike that case, this just gets more and more and more complicated. Every time you do it, this thing splits into two things, right? Because it's a square, and you just get more and more and more pieces, and 2 to the n terms. The n term that you can make hardly any sense of it, and they're all completely uncontrollable things, right? Okay, so nobody was able to do this until Martin Heyer noticed that if you take h minus h6, you call that u, then dtu. So what he noticed is that if you do this, and now you look, nothing seems to be getting better, but if you look at the differences of these equations, if you look at the differences, so hn minus hn minus 1, actually, it's like they're all satisfying KPZs, but forced by things which are getting slightly better in regularity. Okay? But it stops at 6, the regularity improvement. So if you write this, then you get this equation like this. Well, it's just going to be like it's just going to be like a KPZ. There's no big surprise here. Okay, but then there'll be a term. Okay, so minus a half. It's the same as it was before, except it's being forced by all sorts of horrible things. And A and B are things you have to compute from the first 6 guys, right? They're just like 4 pages long, each one. Horrible nightmare. But he was able to prove that this makes sense. So this is a unique solution of a certain fixed point problem.
So what did you learn from that?
Maybe it's better if I answer that after I do something else. Well, at least you know that KPZ is well posed, but you learn more fixed point equation in a space of rough paths. And this is really truly difficult to prove. Okay, so there's a sense in which KPZ is well posed. Okay, and more important, the answer is the Hofkohl solution. Okay, there's no question the Hofkohl solution is the answer. Okay. Okay. So now that you've got all this, let's talk a little bit more about rescaling. Okay. So scaling. I don't like that blackboard. So now that it makes sense, we can start rescaling the equation. Scaling. I can just do rescaling. So I'm interested in if I start with KPZ, and I don't know if it's even written on the, okay, so I'll rewrite it. Okay, so we start with KPZ, and then we want to let h epsilon tx be a rescaled version of the KPZ. So I'll just put some scalings, maybe some epsilon to the b in front, h epsilon to the, what did I call it, minus z t epsilon to the minus 1x. The reason we're doing that, we're always interested in probing huge scale. So epsilon's supposed to be a small parameter relating the big and small scales. Okay? But I just want to write an equation for this guy. Okay? So this is just simple scaling theory, but it's all okay because you know that KPZ is just the solution of this. And everything will be true modulo the constants changing with this epsilon, which isn't the same as that epsilon, right? So you get dt h epsilon. So this is just a question of where all these things rescale to. And so you get half epsilon to the 2 minus z dx squared h minus half. Okay, now epsilon to the 2 minus z, minus b dx h epsilon squared, and plus epsilon to the b minus z over 2 plus a half. If there's a mistake, I can't even read what I wrote. So, okay, so it's not too hard to correct a mistake if there's one. But so this is just simple scaling applied to the thing. Except of course the white noise scale is like the square root of things, right? Because it's okay. So otherwise there's nothing very deep here. So we're just going to read off from this thing what scale we should see interesting stuff. Okay. Now, as before, we know that if we're going to see something non-trivial in the limit, well, then we should see something non-trivial at time 0, and at time 0 it could be Brownian motion. So there's only one chance for B. What? In T, yeah, the T and the X of the white noise scale exactly the same way because it's both white noise. It's completely symmetric. Okay. Yeah. So and the B just came from the DTH, right? So that's the halves of it. So so you certainly believe that B has to be a half. So again, this is going to be one of these slightly fake arguments about the long-term scaling. So the long-term scaling, you guess that B is a half from the Brownian motion being invariant. Okay? This comes from Brownian motion. Comes from Brownian motion invariance. And you can see immediately that if B is a half, there's not too much you can do with your Z. If B is a half, Z is just forced to be 3 halves. Okay? Because if you choose Z to be anything smaller than 3 halves, everything just goes to 0. And if you choose anything bigger, this guy goes bananas.
But on the other hand, you choose Z equal to Z, and there's violate the Brownian motion scale.
What?
I mean, the Brownian motion, the X and T are supposed to be scaled like one is epsilon minus 1, the other one is square root of epsilon.
No, it's not Brownian in time.
No, you're confusing different X's and T's. You see, the Brownian motion in X. Actually, oh yeah, I should just tell you what these things look like. Yeah, that's actually important. So what happens to an equation like this, actually, there's a general theory about the Z's you can check pretty quickly. Because the Z, just checking from this guy here, if you want to know what Z looks like, you just check what this looks like in X and T. In X, these things look like Brownian motions. So they have Helder about 1/2 minus. But in T, it's much worse. It's about 1/4 minus. Okay? They don't look Brownian in T at all. Okay? And this is an easy thing to check, as I said. You just check it here. Okay. Okay. So, yeah, so we're not talking about T. Okay, so that forces this Z equals 3 halves. Okay? So this is the true scaling. And of course, that's the same scaling I talked about yesterday. That just says that the space, the scale of the fluctuations is 1/3 of the time, right? T to the 1/3. So that's the T to the 1/3, and this 3 halves just means the same thing. Okay? The fluctuation, the size of the fluctuation here is the epsilon to the B, right? So epsilon to the B, if that's epsilon to the 1/2, that means the fluctuation of this object is about epsilon to the minus 1/2, which is 1/3 of this, right? Okay? And then in space, we said this scale is supposed to be T to the 2/3, and T to the 2/3 is epsilon minus 1. So this is just a rephrasing of all that. So this is just a different way to see that same thing. Of course, it's the same input, too, so it's not terribly surprising. Okay, so this is the true scale. That's a true KPZ scaling. And so what you expect is that modulo, now of course, when I do this, it's this thing, modulo the huge constants changing like crazy, right? This big constant, C epsilon minus 1, now became, so the C becomes a new C. So modulo subtracting enormous constants under this scaling, so you're supposed to see epsilon to the 1/2 H, epsilon to the minus 3/2 G minus 1x minus some enormous constant, which I don't even want to think about. This is supposed to go to some universal object, right? Yeah, of course. Yeah. And actually, in a lot of them, you can see it's funny. They really all look like a C epsilon minus 1 with some funny C. Of course, C epsilon minus 1. Well, okay. Now, now, by the way, if you look at this thing, actually, maybe I should write out just with the guys rescaled. So you get dt epsilon equals minus a half dx h epsilon squared. I'm doing something stupid. You can probably read it for yourself upstairs. But you get epsilon to 1/2 because 2 minus z, that's a half over 2 dx squared h epsilon plus epsilon to the 1/4 c. That's the equation you get. And so it's pretty tempting to just say, as epsilon goes to 0, it goes to Berger's equation, right? Well, integrated Berger's equation. But that's, whatever that means, you know, Berger's equation is not very well posed. And it's not the entropy solutions, that's for sure. Because if you check entropy solutions of that equation, you can even start with Brownian motion, there's no problem. And actually, you don't stay Brownian. So that's not correct. So it's some sort of funny version of that. Okay. Okay. So that's the real scaling. So that's the sort of KPZ universality class scaling of KPZ. Okay? Yeah.
So you keep the scaling of the quadratic term correct.
Yeah.
And then,
And you let everybody else go away.
yes, so even the noise term disappears.
Yeah. Yeah.
But I can also choose to keep some other term y to u.
Yeah, okay, let's do that. Okay. So, or and that's right. That's right. The equation itself is not scaling invariant. Okay. But the question is, what else are you going to do? So you could say, well, yeah, let's keep the dxh squared. Okay. Okay. So, or let's put z equals 2. So let's put z equals 2 and find out what happens. So if you put z equals 2, I'll just write them out because it's a little bit hard to read. So you get dh epsilon equals a half dx squared h minus a half epsilon to the minus a half dx h. Oh, there's epsilon squared. And then I guess z equals 2, that's okay, right? B's a half, yeah. Plus xc. Yeah. So. Well, certainly, yes. That's right. That's right. If you take epsilon to infinity, then there's no problem. If you take epsilon to infinity, then you get what you should get, which is just the linear theory, right? And so that's a small time or scaling into the thing. Okay, but we're only interested in scaling out. So what are we supposed to do about this? So that looks like that looks terrible, right? How are you going to get rid of this? But actually, it's not. So this is the funny lesson. Or you could start. Yeah.
Then the nonlinear term will disappear.
No, look.
Suppose you choose to keep dx.
No, that's what I did. I did that. That's the Laplace operator just means z equals 2. So that's what I did. But then you get in trouble, right?
Well, it disappears when
Epsilon goes to infinity. Yeah, it disappears. That's right. That's right. That's right. But let's let's agree among ourselves that we're not interested in epsilon goes to infinity. Yeah, sure.
And we're interested in the
Yeah.
but there's a whole in the
But now I want to show you an intermediate fixed point. There's something in between, okay? So, or you could do something really funny. You could start, instead of starting with KPZ, start with a rescaled KPZ. So you'll see, this makes sense, okay? So I'm going to start with KPZ with an epsilon 1/2 here. And then that goes away, right? You choose z equals 2. Okay, now that looks ridiculous. It's just cheated, right? But there are models which have an adjustable nonlinearity. And I can just adjust, sorry? They're models with adjustable nonlinearities. I'm going to show you. So ASEP, asymmetric exclusion, there's the Q and the P. And Q minus P is actually the nonlinearity. So if I choose Q minus P equals epsilon 1/2, and I diffusively rescale, this tells me I should get KPZ. Okay? Sorry? With Z equals 2. Yeah. That's what it's called, diffusive rescaling, right? So e.g., I'll state the theorem. And I could probably almost prove it. So start ASEP. So any model you have with an adjustable nonlinearity, this should work, but there's not too many. Okay, start ASEP with Q minus, I don't mean start ASEP, consider ASEP. ASEP with Q minus P equals epsilon 1/2. And then so you take the height function of ASEP, and Q minus P is 1/2, epsilon 1/2. And now we'll take epsilon 1/2 in front. This is what it said we should do. And then epsilon minus 2t and epsilon minus 1x, right? And then you have some crazy constant, and don't even worry about it's really crazy, will converge to KPZ. And this is true. This is a theorem.
Is there a non-integrable? So this looks much easier than all the other things that we were talking about. Is there a non-integrable model for which this for which one can prove that these are
This type of convergence?
yeah.
Yeah, that's true. Yeah, you can do this for some non-integrable cases. This has nothing to do with the integrability of ASEP.
So what
They have to.
But that's a different universality class than that one.
Sorry? There's just too many questions all at once. It's just, which one's this?
This converges to some universality class, but it's different than this one up here, up on the top one.
No. This is KPZ.
That's the same one.
That's the solution of KPZ. So, the honest to goodness KPZ, the log of the stochastic heat equation. So this is a. If you take ASEP and you do that scaling, that's a theorem. It converges to KPZ under very, very general conditions on the initial data. So back to your question. You can do this for, I know, the one I said at the beginning. The one where I took the, so recently we proved that did I erase it? Yeah, no, I erased it. When I took the nonlinearity and I smoothed the nonlinearity so that we can do that one now too. And well, you asked, maybe it's integrable, I don't know. But that's not what we're using.
So what's the statement about that one again?
Oh. You want this? You want the exact statement for?
So you took the regularized one, you're saying?
Yeah, the regularized one. That we can. That if you remove the regularization, it converges to KPZ. Yeah. So maybe it's not exactly this statement. Sorry. So you want a non-integrable model with an adjustable nonlinearity that you can prove converges to KPZ. Yeah, there are. Just a sec. Let me think about it a bit. I'll produce one. It doesn't. There will be many soon. How about that? Right now, the proofs are relying on some special trick, which may have to do with integrability. So it's a little bit of a fussy thing. Okay. Oh yeah, no. Sorry, I'll give you one right now. Sorry, I'm being stupid. Okay, but it's slightly different than this. Okay. Morally the same. Yeah.
So in ASEP, if you have Q equals P, you find the nonlinearity goes away
Yeah.
completely. So is there a way of seeing that?
Yeah. If you put a C here or put a gamma, then you'll get the gamma here. And the gamma goes to 0, they didn't do anything. Yeah. No, there'll be a gamma and there'll be some gamma in the x. Yeah. So when you no, it's as simple as that you would rescale out the nonlinearity. You'll go to it. How about this? I'll put the gamma. It'll go to gamma, and gamma will be in front of the nonlinearity. That's all. It's really just that simple. Okay? So if you put a gamma there, it's just that gamma in front of the number. It's nothing more than that. Okay, so yeah, so there's another thing you can do, and that can answer your question. So because yeah, I really wanted to keep the diffusion, so we could take z equals 2. And this looks a little weird, but just forget about the b equals a half. Just take b equals 0. Okay, if you do that, then, well, let's just see what you get. You get dt h epsilon equals a half dx squared h epsilon, right, minus a half. Okay, so now you see the nonlinearity is okay, actually, because b was 0. So dx h epsilon squared. But now it's the noise that gets mad at you, right? So z equals 2, there's no b equals a half, so you get plus epsilon minus a half c. Okay? So what you could do is, again, you start with dth equals a half dx squared c. Plus epsilon 1/2 of the noise, and then you'll get this. Right? Okay. So this thing is called, this thing here is called the weakly asymmetric limit, for obvious reasons. And this limit here is called the intermediate disorder limit. Or the small noise limit. Okay, so both of them, so if you start with a small noise or if you start with a small nonlinearity. Okay. So I should show you a model with an adjustable noise. They're actually much easier to produce. If you take the directed random polymers, then, so the directed random polymers, we're looking at the partition function is just this expectation of e to the minus beta, and then you have the sum of the ci xi, I equals 1 to n. Right? And then the noise, of course, is just the power of the noise is beta. Right? So if we call this z beta and x, so it's just x and, okay. So that just means you start the pass at x, or maybe you go to x. It doesn't make much difference. Okay, so you've got this z, b, and x, and then you should take the log, because that's supposed to be KPZ-like quantity. And now you should just set beta equals epsilon to the 1/2. Right? That's what it told you to do. And now you take the n is epsilon minus 2t. Right? Of course, it should be an integer. You take the integer part of that. And then you take it epsilon minus 1x. Right? That. And now we just subtract off some constant. The constant here, in this time the constants are really, really complicated to compute. But anyway, start with that. And I just want to check and make sure I'm stating it correctly. And I have to put a minus sign because it's a minus sign, because I want it to be the same KPZ. And then there's a 2. Don't even worry. Add that 2. And that actually converges, again, to KPZ. So that actually converges to that's KPZ. So that's the theorem. And now this maybe answers your question, because you don't need an integrable case. This is true in almost complete generality. This is true as long as...
So the justification
of the X's. Yeah, these are IID, of course, and to prove it, okay, so the situation is in the proof, we assume that there's 8 moments. Or maybe a little bit, 8. Sorry. We assume there's 8, but actually you should only need 6. And I sort of know how to prove with 6. It's so funny. It's very easy if you have 8. But the main point is that's it, nothing else. It's a complete general thing. And this one should be 2, except there's a technicality. I can even try to show you the technicality. Okay.
For undirected, you can, for something which, if you don't have an integrable model to compare with, there's no, even in the scaling, there's no, for undirected.
No, yeah, nobody knows. No.
So you know this because you're scaling, right? I mean, if I didn't scale and I asked for, because you're taking some limit, small epsilon.
Yeah. So the picture looks like this. There's this big KPZ universality class. And all your favorite models are there, right? And in that universality class, there's the proper scaling, which is the KPZ scaling, which is this. So you should do that renormalization and subtract off constants. And then there's some fixed point in the universality class, which nobody knows what it is, full of Airy processes. And all your models are going to scale into this fixed point under that scaling, right? Under the true KPZ scaling, right? So all your models, I'm not going to write down all the models. All your models think are in KPZ class. But then there's a funny model, KPZ itself, KPZ equation. And as far as KPZ universality class is concerned, KPZ equation is just the same as anything else. It's just a model which was designed to make mathematicians crazy because it has a bad nonlinear, funny thing. But otherwise, it's just another guy which scales into this same fixed point, right? Okay, but there's a funny thing because there's a mini universality class, a toy universality classes. So if you take these directed random polymers, they're there. Okay, so the big theorem is that the directed random polymers under the true KPZ scaling should converge down to here. Nobody knows how to prove that, except for integrable models. That's the true thing. But you can do a toy thing, because you can rescale these guys in this blue scaling, in this weak scaling. You can rescale them here, right? This is the intermediate scaling. Or you could take ASEP. So you take ASEP, and ASEP has this adjustable nonlinearity, so you can do the toy scaling to him too, with this weak scaling. So these two weak scalings are different, but they're close in nature, right? And they scale to the KPZ equation. But see, the thing is that now that means that if KPZ equation itself is something you can study, then it's actually better than the other models because it has its mini universality class, which the other discrete guys don't, right? So you can actually infer some information, right? So if I prove some asymptotic fluctuation result about KPZ, then you can just go back through that fluctuation result. So now if I know the distribution of H, that means you have some sort of universal result about Z, that their asymptotic fluctuations are GUE-like, right?
I don't understand, but for H, you also want to know a large time behavior.
Right.
So you have some interchangeable problem. You cannot study the large time behavior of H from these models.
Wrong. So what happens is, that's not correct. So what happens is that some of these models, like ASEP, so now in this class, there's a few special things. So this guy's a special one. And then even in directed polymers, now I've done it in a bad way, so maybe directed polymers would be a little universe over here. Okay. In directed polymers, there's a special one or two, like the O'Connell polymer or the log gamma polymer. There's a couple of solvable cases. Solvable. Solvable here means semi-solvable. Okay. Now there's some really solvable things. I don't know what to say. You know, like TASAP, that's really solvable. These guys aren't as solvable as this, but they have some solvability. And that's,
Why don't you put ASAP as just ASAP with some, why isn't it just a special case of ASAP?
okay, so there's, wait, there's an ASAP universe. There's an ASAP universe in which there's a super solvable version at one end. Okay? But that guy can't be scaled to KPZ. You understand that? There's nothing you can do. You don't have the adjustable parameter. So that's why it's so important to have these solvability results about ASAP as opposed to TASAP, right? So for a long time, the exact results were about things like last passage percolation, the beta equals infinity, or TASAP, which are special solvable models, but they can't be rescaled to KPZ. So they're sort of stuck where they are. You just have the result about them. But there's a big advantage of getting KPZ, because once you have KPZ, so if you have, so you start with some semi-solvable model. You get some result for KPZ. But now you know this. So that means you get some information about all the directed polymers. Maybe not exactly what you wanted, but something, right? Yeah. Okay.
You want to study the HTX for T and X large.
Yes.
And now, but now you get this from this spatial scale. But still, so then you still answer the T and X large question in the original part.
Right. Okay. So let me show you how you do that. Okay. Okay. So I have 10 minutes. So how do you do that?
This means in the original model, you have to be able to do it for extremely long time or whatever.
Just a sec. Just hold your horses. Okay. So you see, how do you do that? Well, maybe this isn't your question. I think it is, though. So I'll interpret it the way I want, right? Okay. So once you have this result, right? Now Tracy and Whittam come along, and they say, look, we can calculate the distribution of H ASAP in a certain case. Okay. So now we take that exact probability distribution of ASAP, right? And you plug inside that scaling, okay? And out of that, you just take a limit. You do the asymptotics of their formula. Should I write down the formula? Do people know the formula?
Of course, nobody knows the formula.
Well, I think I'll write it down because it's.
Why I'm asking is
Yeah.
really just some uniformity. So some uniform.
You're asking an analytic question. Yeah. Okay. Okay. Okay.
You have to be able to keep this control uniform for T and X, otherwise you cannot really take a limit from your convergence. All I'm saying is your convergence cannot be just for T and X fixed, then you have this convergence. You have to be able to do
What you mean is that.
this convergence has to be very strong.
Yeah, sure. Exactly. But what we do, so there's a formula. Okay, maybe I'll show you the formula because at least you get some idea. Okay, so this is the Tracy Whittam for ASAP formula. So this is the height function of ASAP. Sorry. And there's a Q and a P. Q and a P are just fixed things. And you ask, what's the probability that this thing's bigger or equal to y? Okay? And this is equal to something. That's the point. Don't even worry. But I'll show it to you just to get some impressionistic idea of what the thing is. Okay, so integral. And there's a d mu over mu. This is a contour integral over a circle slightly less than 1. I don't want to write that down. Product, this k equals 0 to infinity. You get 1 minus mu tau to the k. There's a tau is always p over q. It's just a parameter in the problem. Okay, tau to the k, and then you have a Fredholm determinant of I minus a kernel j, and this is acting on L2 space of another circle a little bit smaller than 1. No, it gets much worse. That's just the beginning. So these guys are variables inside that circle, and then that thing is given by another integral But this integral is slightly bigger than 1. Okay. And there's a lot of constraints about where these contours can actually be moved, and which are as important, but I won't talk about that. Okay. And then you have a summation. This is a really crazy function. Tau to the k, zeta over eta prime to the k over mu minus tau to the k. And then you get d zeta over eta prime, zeta minus eta. Okay. And then I didn't tell you what the size are. So the size are, they're actually simple enough. Okay. So the miracle of this formula is how simple it is. Well, actually, tau just means P over Q. It's just so I don't have to write P over Q all the time. Okay, I think everything's there. Okay. Now, so, I mean, this formula is it's unbelievably simple if you think that the way it's done is by calculating using beta ansatz k particle to k particle transition probabilities. So you take k particles and you ask what's the probability they start here and they end here. And that's given by a k-fold contour integral. And that's not so hard to derive. But then to get the formula, sorry, and I should say this. This is very, very special initial data. This is starting with, this is half filled. So you start with, I draw it schematically like that. So on this side, they're all particles. And on this side, they're all holes. And this is 0 in the lattice. So every positive integer has a particle initially, and every negative integer has a hole initially. And then you get this formula. So you have to sum those transition probabilities. The thing involves an infinite sum, which for some unbelievable reason all starts decoupling. And then you arrive at a remarkable formula like this, which is actually you arrive at a much less remarkable formula, which then needs a lot of post-production to turn into something like this. So it's an amazing formula. Now, so you have this scaling. And the scaling just means you have to you can just see what you have to choose the y to be this epsilon minus a half times this constant, right? And the constant is computable. It's very complicated. And then you choose the q and p is epsilon and a half, and then you choose t equals epsilon minus 2, right? And then you just take a limit. And when you take a limit, you just get an exact formula. So you see there's nothing uniform one has to do. You just actually get a form of the probability HTX is greater than R is equal to, okay?
I thought the formula is a symbolic form, exponential scaling function, whatever, is another.
Let me just figure out which board I'll write it on, because I used that. Okay, so maybe I'll erase this. Let me just write the formula, because then you'll see. So you literally get the following thing. Now, it's a little bit unclear if you start with this initial data, by the way, what is your initial data for H? That's weird, right? Okay, so that's not at all clear. And actually, the initial data for H really is weird. And that's because H is a weird equation. H is not a norm. It's really Z which is the equation. And the initial data for Z is sensible. So the initial data for Z is just a delta function at 0. But then you take log of a delta function. You don't know what you're talking about. So, so for that special H, you get the probability HTX. Okay, it comes out a little bit goofy. Minus 2 over 24 plus S is equal to. So the main point of this formula is just trying to answer Yao's question by writing down a formula, but. I'm not trying to avoid your question. I'm just saying that you just get an answer. There's a certain distribution. I can tell you what all these things are. L2.
There's no epsilons in the equation anymore.
They've all disappeared, of course.
By a limiting process, or do they just exactly go away?
They all go away. They have to. Because that converges to an object which has no epsilon anymore. It's just literally the h of KPZ.
They converge to zero. They're not just absent to begin with.
I'm not sure what you mean, sorry.
Isn't the question about interchange of two limits, or did I understand that incorrectly?
I thought even this HTX formula you want to understand asymptotic behavior, not for fixed T and X. Because this is solution of KPZ.
Yeah, just a sec. This is, so what you get is a formula for the distribution, the one-point distribution of KPZ, starting with that funny initial data. And that's the curved geometry where you're supposed to get GUE in the limits. Okay, so you get this weird formula with this kernel, which is just a deformed area kernel. T to the 1/3 x plus s y plus s ds. Okay. So you get this exact formula, which is, it's not terribly helpful, but there's an exact formula for the probability distribution. And this is a trace, this is kind of a goofy object. It's a trace of the kernel inverse, and this is a projection onto the area operator. But it's not very hard once you have this formula to check that as t goes to infinity, the thing you want, which is that you want htx minus some parabola, right? Minus t over 24, divide by t to the 1/3, and then there turns out there's a 2 to the 1/3, which is annoying. It goes to the GUE, largest eigenvalue of GUE, right? But that's just an asymptotic you do in this formula. And it's even you can sort of see that it's going to work, right? It's all set up for it. Well, of course, we made it set up for it. But this thing, you can see what happens. As t goes to infinity, it just goes to a step function, which becomes the area kernel. And so the only hard thing is just to see why this trace drops out, which is it's not terribly hard to see. And the funny Gumbel transformation disappears. And you just get the determinant of I minus k in the limit, which is just the, so that takes, it's really an hour's calculus to just check that the limit is the right limit once you have the formula. Okay? That was your question, right? It was, right? Just because you have an exact formula. Yeah, so that formula is just, that's this formula plugging in all these crazy variables and taking a limit. Now that's really tricky. This thing badly does not want you to do that. Everything is as critical as it could be. Every single thing tries to avoid you doing that, but that's what you get after you compute for a while. Okay, so the whole game is to get models. And so now there's this ASEP. Now there's this version of ASEP called QTASEP, which is sort of a different. Oh, actually, it should be written like this, QTASEP, because it's just a different deformation of the TASEP. But it has sort of the same properties that one can get formulas for it and then rescale them to KPZ in this way, right? Okay, or you could go directly here. You can do this too from the ASEP, right? Because once you have the exact formula, you could do that. You could do that from the TASEP, okay? Or you can do it from the special directed polymer. You could go here. So these are sort of the known cases. This is the log gamma polymer, which turns out to be a special solvable one. And the problem with all this is that it's terribly, terribly dependent on initial conditions. So if you want a formula like this and you say, well, I want some different initial condition, well, good luck. You don't get it. So what we're doing right now is, what's your next initial condition you would want? Is is this one, is this particle, hole, particle, hole, particle, hole, because that's the flat initial condition, and then you're supposed to get GOE. Okay? So we finally got a formula like this, but it took a couple of years. And it's not like you're going to get one for any initial data.
Analog of that formula, or is the analysis of that formula?
No, this formula is just for the flat.
Okay, yeah.
It is not the case that if you ask for your some other initial data, Tracy and Whittam can give you a formula. They can do this, and they can do, instead of being full here, you can put them in randomly here. That's the other case.
Oh, you can do that.
Yeah, so Bernoulli over here. So actually the full is just a kind of limiting case of that. That's the actual solvable case with this type of formula. Okay, and so that you can rescale, and you get KPZ starting with sort of half Brownian motion. And then you get an exact formula for that. Okay, so those were the first two done, and then you ask, well, what are the other initial data for which you might be able to do this? Well, start with Brownian, start with flat, and the two will come out in the next few months, but it's taken several years to get the analogous formulas.
And they're much more complicated?
Actually, the flat formula is much simpler, but but much harder to work with. Yeah. Sorry.
This amounts to solving basically Berta ansatz, right? Complements.
Well, no, it's much more, because the way the beta ansatz is used. I'm sort of over my time, so you guys can tell me to stop talking. But the way the beta ansatz is used in Tracy Whittam is to actually compute transition probabilities. But then you have to perform this enormous summation over these things, and that's really the difficult work. So there's this formula sort of comes out of a sequence of combinatorial miracles over several years. And that's not something you can replace with for other initial data, right? So the beta ansatz gives you a formula for, it doesn't matter what your initial data is, because you have 10 particles, you want to go to 10 particles, you can solve that. That's the beta ansatz part. Yeah. And now the new theory, which Borden and Corwin have, is what they have is a thing to tell you, if you have some initial data, then here is a clear problem you can solve. It's sort of a beta ansatz problem to tell you how to compute the moments of ASEP or QT-SEP. It's sort of similar. But then you find out you can't solve it except for this case. And then finally we solved it for this case. It's like these things just happen to have solutions in a few special cases. So this idea that KPZ is solvable, it's not exactly solvable. It's been solved. 1-point distributions have been solved through one initial data, and now maybe 2 or 3. There's a couple. Yeah.
If you are initial data, you don't need to go to GUE or GOE. How comes you can have a good formula?
Yeah. So in some sense, what one believes is that the formulas must be coming because of some magic, which has to do with the fact that these are sort of scale invariant initial data. Like when you do the scalings, which I talked about earlier. So where's the big scaling? Oh, I erased it. So when you do this KPZ scaling, of course, that rescales your initial data. So the only initial data which will somehow be right are ones which are scale invariant, right? And that sort of picks out Brownian motion, flat, and this special initial data. So those are the 3 scaling invariant things. Or you could sort of have one of them on one side of the origin, one on the other side of the origin, because that's still scaling invariant. So you get 6. There's 6 special initial data, and if you start with those 6 initial data, there's 6 Airy processes which are known, which you get. So that seems, and they're all given by determinants, just like. So that's sort of the different initial data classes.
I think there's really only those classes, universality classes of initial data.
No, that's not true either, because you can produce other things which are invariant, which are weird, and might be solvable. In fact, I think some of them have been shown to be solvable, and you just don't know what to say about them. They're sort of, so that what there probably is there's lots of little weird universality classes, except 6 basic ones, and those are the domains of attraction of most everything, something like that.
Now over here you drew the KPZ as a fixed point and the KPZ universality class as a fixed point. And I thought you said,
Oh, sorry, the blue is, so I shouldn't have drawn those in blue.
well, yeah, that's
Yeah, okay.
but those two fixed points that things are flowing to, at this point,
Under different maps. Under very different maps. So there's the
Yeah.
white map. I made a mistake here to draw those in blue, right? So those ones are white. White means, yeah, that's white. White means so white here means this scaling. So every model has something like a free energy. And white means this renormalization, right? Okay.
blue is some other scale.
Blue means the two funny things I wrote, the weakly asymmetric scalings. The weakly asymmetric and intermediate disorder scaling. Well, so no, so just remember, the flow, it's not one flow. The blue flows are different than the white flow.
Yeah.
Okay, so the white flow is this thing, the real thing, right?
Yeah.
And the blue is this weakly asymmetric, this toy diffusive scalings, okay? So in the weakly asymmetric scaling, you'll always get KPZ, because it's invariant under that action, okay? So in a sense, they shouldn't be on the same picture. So that's one type of flow, and this is another type of flow. For a model like ASAP, you could prove either, okay? Does that make sense?
Doesn't it follow that KPZ also flows to that?
Yeah. It's just the picture's been erased too many times. So
So that's not in doubt. That's proven, or not? Yeah,
for this special initial data.
for special initial data.
For this special initial data, and in the sense of one-dimensional distributions. So there's still plenty to prove if you want to prove it goes to that point. Yeah. So
you know very little about that.
right. So the fact that goes to GUE is one type of that convergence, right?
Tiny piece of information.
Yeah, exactly.
But you don't have the white line for KPZ going to KPZ universality.
Yeah.
He has that.
We have one example of that, which I just showed you. This thing
Okay.
for the special initial data going to GUE.
That was ASAP, not KPZ, right?
No, this is ASAP. So I take ASAP, I rescale ASAP. That's a formula for ASAP, right?
Yeah.
I rescale ASAP like that, and I get KPZ. So I rescale this formula like that, and I get an exact formula for KPZ. Exact. It's just KPZ has this distribution, starting from that initial data. And then I rescale KPZ and you get GUE. So that one case, one-point distributions converge to the right thing of the KPZ universality fixed point. It's a kind of, I just want people to understand. It's not as, we haven't exactly shown KPZ is well, integrable. It's one initial data, one point, right?
Next week, Borody is going to give 2 lectures, and so next week we are not going to continue this thing because Borody is going to give 2 lectures. But there's some question.
So is there some more description of this question mark in the middle? Because what you did is that you did a one-dimensional distribution, identified one-dimensional distribution. Yeah, exactly. So the question mark, is there some other description of the question mark? Right. So so this is this KPZ fixed point question. So what does one know about it? One knows this GUE point, the GOE. So one knows that for fixed time and these special initial data, it should be Airy processes in X. Right? Okay. Nobody's proved there's a fixed point or that it's unique, but given that it is, given that, then it would have these Airy processes as its fixed time marginals. And actually, they're just if you start with this scaling invariant initial data, you can see that it'll just be rescaled Airy processes as you go along. So you sort of know what it looks like for a fixed T. So then the question is, what is this thing? And we have some. I don't know if you call it a conjecture. We have a vague conjecture which is true, and a precise conjecture which is probably false. for what this thing is.